Hi, welcome back to the channel. So I had a bunch of people email me and ask for my analysis of the two new videos brought out by Peter on his Raptor NG design. So here it is. So I'll start this one out like some of the previous videos I've done on Raptor with the claims that Peter's making for the new design. 300 knots on 11 gallons per hour. That'd be with diesel engines rather than spark ignition. Los Angeles to Hawaii range on only about 80 gallons. Vertical takeoff and landing. To be certified and sold for $100,000 to $130,000, depending on whether VTOL or not. Hopefully to be built by Ford. Projected to build 30,000 units a year. Box wing design will fly the same as Raptor 1. And it'll be driven by a revolutionary rim-driven ducted fan design, which will be massively more efficient than anything seen before. So we'll examine these claims a little bit here and see what you think. Since the last iteration of Raptor NG, the fuselage has been widened and made larger, about 2 inches in all directions. You can see how wide it is now. Presents a lot more frontal area and more wetted surface. Certainly going to have more drag than it did before. And the other big thing is the ducts have been made movable now and another one added in the nose to give it vertical takeoff and landing capability. So that's a big change. Peter has his eye on using a couple of these opposed piston swash plate type engines from Spain. They're pretty unproven, and that's usually not a good combination to use with a new airframe and a new propulsion system. As with most new engine designs, they make a lot of claims for them. And this one here, it's just anytime I see market disruption from some new company, I just kind of cringe or laugh. So this new company thinks that they're going to license or build 226 million units by 2027. I don't think so. Total worldwide automotive production is about 30 million units a year. There's no way everybody's going to switch over to this engine. That's just marketing BS and wishful thinking. I'm not sure how this company patented this engine because a friend of mine patented a very similar engine back in the 70s, Dr. Christensen, and built a couple prototypes which ran. In any case, this has been in the public domain for decades now. Engines aside, we'll move on to discussing the revolutionary fan design that Peter's come up with. This is a rim-driven hubless design, as you can see here, so it has no center to it. And you can see the specs that he's claiming here for it. So the fan is electrically driven by electric motor mounted in the periphery of it. Power for the electric motors comes from a generator, which is driven by the gasoline engine that we just saw. This design is nothing new. The concept came out in about 1940, and it's been used in the marine industry for a couple of decades. And it's been discussed for aircraft as well here, as you can see. Now Peter's used his proven CFD skills to develop a fan which produces almost twice as much thrust per horsepower as this fan developed by Airbus and their E-fan, which we've discussed before in a previous NG video. Peter has come up with a rather ingenious variable pitch mechanism for the blades here, and that could be very useful in a ducted fan to operate over a wide speed range with good efficiency. CAD model is one thing, implementation in real life will be something completely different and more complicated. The prototype just has fixed blades and it's only been tested to about 100 RPM. Obviously you can't draw too many scientific conclusions from that, but he did build it and it's pretty cool and it's a starting point. Okay, this slide here is about fan characteristics or fan law. So this looks at the relationship between fan RPM, fan diameter, flow, velocity, etc. So the mass flow is proportional to RPM. If we double the RPM, we double the flow. Fan input power varies as a cube of the RPM, so it requires 8 times the power to double the RPM. That's significant. input power varies as the fifth power of fan diameter, so it requires 32 times the power if the fan diameter is doubled. Thrust varies as the fourth power of the fan diameter, so diameter makes a huge difference in thrust. Thrust varies as a square of the fan RPM, so if we double the fan RPM, it gives us 4 times the thrust. Thrust equals fan pressure times fan area. Exit velocity is proportional to fan RPM, so if we double the RPM, we double the exit velocity. And exit velocity is also proportional to fan diameter, so if we double the diameter, we double the exit velocity as well. So this photo is just illustrating the extreme technical difficulties of designing a rim-driven fan system of this diameter. So the surface speed at this edge here at 5600 RPM is 586 feet per second. And if we were using 2-inch rollers here, these rollers would be going almost 68,000 RPM. So you can't find bearings that will survive at that kind of RPM at all. And how are you going to integrate them here? This Delrin wheel here, Peter thinks that's going to work okay. It might work okay at 100 RPM like he's testing. It's not going to work with hundreds of pounds of force on this roller. And I'm not sure what kind of bearings he's going to use. They do have magnetic bearings, but they're very bulky, very expensive, and I think impractical here too. Okay, here's a bearing application chart from NSK Bearings. It just looks at load, diameter, dimensions, and RPM capability. So if we used a 2-inch bearing, it's about 52 millimeters, and the grease type, that's what would have to be used here. You can't have external oiling on this type of setup. It's only rated till 10,000 RPM. And even if we went down to about a 1-inch bearing, 26 millimeters here, and fitted a ring to bring it up to 2 inches on the OD, it's still only rated to 22,000 RPM, which is about 1/3 of what's required here. So right there's no bearings that exist that can take anywhere near that kind of RPM. Even ceramic bearings, marginally better than these steel bearings here. It's nowhere close to 67,000 RPM. So the next part of this video is going to reference this paper, which is on the internet, published by 3 engineers who are involved in this technology. So I've highlighted a very important takeaway from this research paper. It's just stating you require very high RPMs on this type of fan to generate decent amounts of thrust. And this part of the study concludes that rim-driven fans can have some pretty high thrust density, but at the expense of very, very high input horsepower. As you can see from this graphic, I'm no artist. However, I'm just trying to demonstrate what's happening with the fan system here. So basically, this is a column of air here. So this column of air is 208 feet long, and it's 2 feet in diameter. So the fan's 2 feet in diameter. And this is, using my calculations at least, this is how much volume of air passes through the fan in each second. So it's a slug of air, 208 feet long, 2 feet in diameter. This is processed every second through the fan. And how we arrive at this, the area of the 2-foot duct is 3.14 square feet, times 208 feet is 655 cubic feet. And it's moving at 208 feet per second, which is the length of this column of air. Peter's calculations, however, claim that it's only 82 feet per second, so that would mean that his volume doesn't agree with the speed or velocity, so his mass flow and velocity numbers just don't correlate. And in order to produce Peter's claimed 1,575 pounds of thrust, exit velocity, like we saw on the previous screen there, would have to be 1,016 feet per second, which is around Mach 0.92. And it's a physical impossibility to move this much air at this speed on only 90 horsepower, as he claims. There's just no way. So this is just showing how I arrived at my exit velocity numbers. The equation is velocity equals 183 times mass flow cubic feet per minute divided by duct diameter squared. We just work through the math here. That comes out to 12,486 feet per minute. We divide that by 60 for feet per second, That equals 208 feet per second, or about 142 miles per hour. Peter's spreadsheet shows exit velocity at only 81.8 feet per second, which is only 55.8 miles per hour. So when duct exit velocity equals airspeed, thrust equals 0, and that's as fast as you can go. So that'll be the maximum speed of the aircraft. It's actually less due to drag, so you'd have to output more mass flow at higher speed, probably to go that speed. And this is far short of the 345 miles per hour predicted by Peter. So here's a chart put out by some professional engineers who are doing evaluation of fan models. And we see the thrust here, calculated thrust, 317 newtons, versus the CFD model results, 212. It just goes to show, even with professional engineers doing the analysis, that CFD models may not be very accurate. Certainly somebody with no background in CFD or fan design, I don't think we can really believe any of the results that they come up with. So this is some of the data compiled by that group of engineers in the paper. And they've gone and evaluated fans up to 500 millimeters in diameter. Peter's fan would be about 600 millimeters, so it's close. We can look at some of the thrust and horsepower mass flow numbers here, at least from their calculated values. So if we looking at a 500 millimeter fan here at 5,000 RPM, it would require about 67 horsepower. This is watts here. If we took it to 10,000 RPM, because input horsepower varies as the cube of the RPM, that would now take 536 horsepower. And down here we have the pressure ratios. You can see at 5,000 RPM, 500 millimeter fan can only produce pressure ratio about 1.04, so it's quite low. That's why these fans have to turn such high RPM to get decent amounts of thrust. However, that increases the power input required considerably. And if we come up here, we can look at thrust. So 5,000 RPM again on a 500 millimeter fan. This is newtons here. If we convert that to pounds, it's only 265 pounds. And if we turned it to 10,000 RPM, we would get 1,060 pounds of thrust. However, the input horsepower goes from 67 to 536. So you can see not too efficient actually for high-speed flight. Down here we've got the exit velocities, 500 millimeter fan again. Speed of 5,000 RPM. This is about what they calculate here, about 155 miles an hour. So that would be the top speed of your aircraft, and probably a little lower than that because of the drag. So if we increase the fan speed to 10,000 RPM, the exit speed would increase to 308 miles an hour, since that's proportional. This would be more appropriate for an airplane like the Raptor NG. However, this is still far short of what was predicted. And down here we got the mass flow rates, 5,000 RPM, 500 millimeter fan again, about 30,000 CFM. That's a little bit short of what Peter was saying in his spreadsheets, but his fan's a little bit bigger and turning a little bit more RPM. So if we turn it to 10,000 RPM, we get 59,000 CFM. So here's a larger version of that fan chart from that study. It's plotting power required in watts here versus RPM versus diameter of the fan. So I've extrapolated the data to 5,600 RPM and a 24-inch fan, which is what Peter was using. We come out to about 415 horsepower required, and that's versus the 90 horsepower that he's projecting. Okay, so here's another equation looking at fan input horsepower. I just plugged in Peter's numbers from his spreadsheet, and using those numbers, his fan design would require 712 horsepower rather than the 90 horsepower that he estimates. Using different equations and different data, we get estimates from 300 horsepower to roughly 712 horsepower, but none of them are close to the 90 horsepower that he estimates. So Edward Fury from Calculator Soup was kind enough to let me use some of his calculators in compilation of this video. It's a great site. go there if you want to find some online calculators for all kinds of things. So here we have probably the most basic equation for thrust in this case. We've used this equation before in the Raptor 1 video, just trying to calculate the horsepower required for acceleration. And it doesn't get much simpler than this. Just force equals mass times acceleration. So I plugged in Peter's values here, and we only come up with a thrust of 127 pounds. That's about 1/12 of what he stated here. So that doesn't make his calculations look very accurate right away. So we're using the same calculator again, but we're using my calculated velocity numbers instead of Peter's. And if we plug that data in here, we get 321 pounds of thrust, which is quite a bit more than we got using his numbers. And finally, using the calculator again, just plugged in some numbers here to look at how Peter could possibly get the kind of thrust he's contemplating. So the exit velocity required to achieve his thrust numbers with his stated mass flow. So I haven't changed the mass flow, it remains the same. Would require a velocity of 308 meters per second, which is about Mach 0.92. So that's 12.4 times the stated number in his spreadsheet. So his numbers just don't correlate at all. And I just have to discuss the concept of disk loading. So the higher the disk loading, the higher the input horsepower required per pound of thrust generated. So if you've got a very big disk or rotor like a helicopter, it can generate a lot of thrust per horsepower. So maybe a typical piston helicopter generates around 11 pounds of thrust per horsepower. And the loading there, so thrust divided by the fan area, is only about 2.6 pounds. Large piston GA aircraft, like a Cirrus, 300 horsepower, about a 6-foot propeller, develops about 4 pounds of thrust per horsepower. And the disk loading is about 42 pounds per square foot of fan area or prop area. And the best state-of-the-art ducted fan's about 7 pounds of thrust per horsepower, with a loading of about 80 pounds per square foot of fan area. Then we come down to the amazing Raptor fan. It supposedly generates 17.5 pounds of thrust per horsepower, with a loading of 502 pounds per square foot of fan area. So it doesn't really seem possible given this. It's got the highest fan loading by far, but generates much more thrust per horsepower than any of these others, even more than the piston helicopter rotor. Highly unlikely to the point of impossibility, in fact. So I think I've shown that Peter's fan values are not realistic at all, to say the least. And in the next CFD image, you'll see this very low pressure zone created by this type of rim-driven fan. It's going to cause a lot of flow distortion and flow towards the middle, possibly backwards. That's not going to give you a higher thrust. And this photo is kind of showing one of the other reasons I don't think Peter's CFD numbers are anywhere close to being correct. These supports here are not modeled at all, and that would make a massive difference in the results, I believe, because this part of the fan is turning extremely fast here, and these things would have to be modeled to have accurate results here. I don't think this rim-driven fan will be able to be built out of aluminum like it's envisioned here, not with these welded blades, and even the outer ring built out of aluminum won't withstand the stresses. It would have to be built out of something like titanium, which would be extremely expensive. What Raptor really needs to push its large, bulky shape through the air at 300 knots is probably something like this GE Honda turbofan. It has about the same diameter as what Peter is contemplating, but you can look at the thrust and weight and RPM numbers. It's turning 19,000 RPM on the fan to develop about 2,000 pounds of thrust. So there's just no way Peter's fan design is going to do that on 90 horsepower. Here's a chart comparing the E-Rex motor driving Peter's RDF system with the Rotax 915 IS and a propeller. So a few things about this. I'm only using 76 horsepower out of the 90 that the E-Rex engine is supposedly capable of. That's because there's going to be losses in the generator, the cabling, controller, and finally the motor before it reaches the fan. And I've also calculated a weight of the whole system there. So this would include the engine, the cooling system, turbocharger, exhaust system, generator, cabling, controller, and fan. And I figure that's about 333 pounds. That's versus the 175 pounds that Peter was using to compare to the GE engine at the end of his video. That's not representative since his 175 pounds is just the fan. It doesn't include everything to drive it like the GE engine, which is a self-contained power plant. And we're using his 1,575 pounds of thrust here, which I don't think is accurate. That results in a thrust-to-weight ratio of 4.73. Then recalculating here using the Airbus E-fan thrust numbers, which I think are really efficient. This would be the best scenario possible on 76 horsepower, same weight. That would generate 505 pounds of thrust, and the thrust-to-weight ratio 1.51. Then using my fan thrust numbers, still a 76 horsepower, still the same weight, I came up with about 271 pounds of thrust. That makes the thrust-to-weight ratio rather poor at 0.81. And finally, we look at the Rotax 915 IS with variable pitch propeller, 132 horsepower at the prop, slight loss through the reduction gear. The weight complete, cooling system, propeller, everything, I figure about 225 pounds. And static thrust, looked at a bunch of numbers from actual testing on the internet, came up with this. Should be accurate, plus or minus 50 pounds or so. It depends a lot on the propeller. And thrust-to-weight ratio is 2.58. That's much higher than this, which is likely the very highest he could achieve. And much, much higher than this, which is more what he's likely to achieve with his design, in my view. So coming back to the claims again for Raptor, it's not going to do 300 knots on 11 gallons an hour. That's ridiculous. It's not going to go LA to Hawaii on 80 gallons of fuel. Also ridiculous. It's not going to lift off vertically because it doesn't have anywhere near enough thrust. It's also a dangerous configuration. If you lost one fan, it would be out of control and would crash. It's not going to be certified. That would cost tens of millions of dollars, and therefore it would cost a lot more than $100,000 to $130,000 to sell it for any sort of profit. Ford's never going to build this. That's just a pipe dream. No one's going to build 30,000 units a year. Cirrus, which is the best-selling piston GA aircraft, only sells 300 units a year. There's no way. This number is ludicrous. And where are you going to find all those pilots with all this money? The box wing layout is radically different than Raptor 1. It's going to require an extensive flight test program, professionally done this time, unlike Raptor 1, to establish that it's safe. It doesn't have any bad characteristics, especially if it's going to be certified. That's going to take a very extensive program. The engine out characteristics of this layout would be quite challenging. Loss of flow from an engine out situation over the wing would cause some pretty interesting results, I think. And you'd have to have probably feathering fan blades as well to cut the massive drag that would have if those blades stopped within those ducts. So all these things point to this being a very poor layout, with multiple issues that would have to be solved to make it safe or viable at all. So to sum things up, I don't see Raptor NG meeting any of its design targets or predictions any more than Raptor 1 did. And to this question posed in Peter's video, could this thruster transform aviation? Well, the answer is categorically no. If he wants to prove me wrong, he should build the actual working prototype running at 5,600 RPM and measure the thrust on a test stand. I think you'll find it's closer to 300 pounds rather than 1,575 pounds. And just a couple of my favorite quotes to end this video off. I think these pretty much say it all. CFD is a very useful tool in the hands of an experienced engineer. However, in the end, all designs have to be properly validated and tested to confirm theories. I could discuss a lot more aspects of the Raptor NG design. However, I'm trying to keep this video under 25 minutes, so I think I'll wrap it up here. Thanks for watching.